Welcome to Virtual CB1A. This is Ma'am Rena, and this is Week 1, Lecture 2 of Mathematics in the Modern World. Today, we will discuss Fibonacci Sequence and the Golden Ratio. Okay, first, let's read the learning objectives. At the end of this video, you should be able to define the Fibonacci sequence and apply the idea of the golden ratio. Let's get to know the mathematician behind the Fibonacci sequence. This is Leonardo of Pisa, also known as Fibonacci. He wrote Liber Abaci and introduced the Hindu-Arabic place-valued decimal system and the use of Arabic numerals in Europe. Just imagine if he didn't introduce the Arabic numerals into the West. We will probably be using Roman numerals when dealing with numbers, which is very confusing and impractical. He also introduced the pattern 0, 1, 1, 2, 3, 5, 8, or the Fibonacci number to the West. The Fibonacci sequence is the series of numbers that goes like this: 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. The next number is found by adding up the two numbers before it. For example, to get 2, we are going to add the two numbers before it, which are 1 and 1. The 3 is found by adding the two numbers before it, which are 1 and 2. The 5 is from the sum of the two numbers before it, which are 2 and 3, and so on. Now let's talk about the rabbits of Fibonacci and the sequence in nature. This is the problem. How many pairs of rabbits will be born in a year, starting from a single pair, if each month, each pair gives birth to a new pair, which becomes reproductive from the second month? Let's follow the legend below to answer the problem. The infertile pair is represented by the blue pair of rabbits. The fertile pair by yellow. The yellow arrow to denote the infertile ones becomes ready for mating. The broken lines for surviving pairs. And the blue arrow for pairs that generate another pair or to map the new pairs to their parents. So let's start with month 1. We have a pair of infertile rabbits. On the second month, the pair becomes fertile and ready for mating. On month 3, the original pair is able to produce a pair of infertile rabbits. All in all, we have 2 pairs of rabbits now. On month 4, the original pair gives birth to a new pair. This is the new pair. While the infertile pair becomes ready for mating. These are the infertile pair. From month 3, they become ready for mating on month 4. Now, we have 3 pairs of rabbits. On month 5, the 2 fertile pairs produce two pairs of infertile rabbits. These are the two pairs, pair 1, pair 2. While the infertile rabbits from the previous month becomes ready for mating. So the infertile pair from the last month becomes ready for mating. This is our infertile pair which becomes ready for mating. We now have 5 pairs of rabbits. Now, let's check the number of rabbits for each month. Month 1, we have 1 pair. Month 2, still, we have 1 pair. But this pair is already fertile. Month 3, we already have 2 pairs. Month 4, 3 pairs. Month 5, 5 pairs. If we continue this sequence, we can have 8 pairs for 6th month and 13 pairs for 7th month. Just like the Fibonacci sequence. Now, let's talk about Fibonacci numbers in nature. For example, spirals. When we make squares with the weeds from the number sequence, we get a nice spiral. Also, the pattern from the sunflower is an example of a Fibonacci sequence in nature. And of course, the number of petals of flowers. Most flowers have 3 petals, like lilies and irises. 5 for Parnasia and rose hips, or 8 like Cosmea. Some are 13 like daisies, 21 like chicories, 34, 55, or 89. Now let's talk about the golden ratio. The golden ratio, in symbol, it is represented by the letter phi, is a special number approximately equal to 1.618. It is also known as the divine proportion. It appears many times in geometry, art, architecture, and other areas such as medicine, dentistry, and music. So the idea behind it. We find the golden ratio when we divide a line into 2 parts so that the long part divided by the short part is equal to the whole length divided by the long part. Okay, let's study this figure. We have this line, the combined blue and yellow, and this is represented by A plus B. The longer line is A and the shorter line is B. So to get phi, the long part, or A, is divided by the shorter part, which is B. And it is equal to the sum of the 2 lengths, A and B, divided by the longer part, which is A. And it is approximately equal to 1.618, or phi. Let's have this as an example. Golden ratio and the concept of beauty. The golden ratio is often associated with aesthetics. Look at this group of rectangles. Which among them is the most visually appealing? Okay, if your answer is A or B, nako, hindi masyado maganda ang taste nyo according to the golden ratio. Kasi si C has the closest ratio to phi. Let's compute. So according to the definition earlier, to get the ratio, divide the longer side by the shorter side. Let's start with A. This is rectangle A. The longer part is 41. If we are going to divide it by the shorter part, 22, the ratio will be, okay, it is your time to get your calculator. Please compute. All right. If you ended up with 1.8636, then your answer is correct. Let's go to rectangle letter B. Again, let us divide the longer side by the shorter side. The longer side is 50 and the shorter side is 15. What value did you arrive with? Alright, if you ended up with 3.3333, then your answer is correct. Now let's go to the third rectangle. We have, oops, let's correct this one. The longer side is 42 and the shorter side is actually just 26. So 42 divided by 26 is equal to 1.6154. Okay, let's compare the three quotient that we arrived with from our computation. The golden ratio or phi is approximately equal to 1.618 and so on. So which among these three is the most visually appealing according to the ratio phi? So the closest ratio is C. Therefore, ito yung pinaka-visually appealing mathematically. This is another example. So which among these rectangles do you find visually appealing? Okay, if your answer is E, then you have a good eye, mathematically. Now let's talk about golden ratio and the concept of beauty. Many buildings and artworks have the golden ratio in them, such as Parthenon in Greece. So they follow the golden rectangle. The golden section can also be found in the Great Pyramid in Egypt. So the perimeter of the pyramid divided by twice its vertical height is the value of phi. Now, let's talk about the golden ratio and the human body. The golden ratio and the human body, as I've said earlier, golden ratio is strongly associated with aesthetics. So, the human body is based on phi. The proportions of the human body ideally, yung mga visually appealing, yung mga maganda yung body, maganda yung features, they follow or their proportions are close to phi. I will not explain the ratio one by one, but you can always pause this video and check this guide. If you want, you can also check your own statistics based on this guide to see if your proportions are close to the value phi, to see if you are also visually appealing. Okay? So next, similar with this part, please pause if you want to check your own measurement to see how mathematically attractive you are using our ratio. This is a detailed guide to see whether you comply with the proportions suggested by the golden ratio. All you need is a measuring device, a tape measure, a ruler. It's up to you. Now let's move forward with the last slide. So this is the golden ratio and the Fibonacci sequence. Let's discuss the relationship between these two. There is a special relationship between the golden ratio and the Fibonacci numbers 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. Each number is the sum of the two numbers before it. When we take any two successive one after the other, Fibonacci numbers, their ratio is very close to the golden ratio. For example, si 3. Di ba sabi natin the longer side should be divided by the shorter side? So, dito naman sa Fibonacci number, 3 should be divided by the number before it to get the ratio that is close to phi. In the first few terms, we have 3 divided by 2 is 1.5. Si 5, divide natin siya by 3, we have 1.66666. And then 8, let's divide it by the number before it, which is 5. We have 1.6. 13 by 8, we have 1.625. 21 by 13, we have 1.615384, and so on, until you reach infinity. And it will approximately be equal to the ratio 1.618. For example, 233, the number before it is 144. So 233 divided by 144, you will end up with 1.61805555556, and so on. And 377, the number before it is 233. So 377 divided by 233, we have 1.618025751, and so on. Okay? So that will be the end of our discussion for golden ratio. And please check out our Google Classroom. I will be posting your activity for this lecture. Okay? So bye and see you next time.